So my name is Jason Gaitonde, and I'll be presenting our paper, Stability and Learning in Strategic Queuing Systems. And this is joint work with Éva Tardos. So just to give a little bit of background and motivation for the problem is for learning in repeated games. So the basic setup in learning in repeated games is that you have some set of agents playing some sort of fixed game. So think of, maybe rock, paper, scissors, or bidding in sequential auctions, or routing with delays. And each agent is selfish, so they want to minimize their own sum of costs over time. And a way that we commonly model agents doing this is that they use no-regret learning algorithms. And sort of the philosophy behind this is, as time progresses and in the initial stages of the game, the agents play some actions, but maybe they don't really know how to play at the start, or even the rules of the game or who the other players are. But by using a no-regret learning algorithm, they can kind of learn from their experience so that later on that the learners will have a better idea of what to do as the game progresses. And the no-regret condition just says a very intuitive thing, which is that for each player I, the sum of costs that they experience over the action sequence is at most the cost they would have faced had they committed to just a single action and everyone else had stayed the same, plus a regret term, where the no regret condition says that the regret term is sublinear in time. And one reason why this, this paradigm of learning in repeated games is so popular is many simple and efficient algorithms actually attain no regret. And it also kind of encodes a very simple behavioral assumption, namely, if that there was just one good action for you to have played the whole time, you should notice it. It's also much less restrictive than Nash. For instance, Nash equilibrium requires some sort of assumptions on players' priors, their beliefs, or their computational power. Whereas, as I said, many no-regret algorithms can be attained very simple and efficient means. And also, many quantitative bounds, like for instance, if you're familiar with the price of anarchy or bi-criteria results, many of these quantitative bounds on the quality of Nash equilibria often directly extend to learning outcomes. So from our understanding of what the cost of allowing for selfish play over centralized control, often not much is lost, and it's not lost in either the Nash case or through learning outcomes. But a critical assumption in this is that a new copy of the same game is being repeated every time. In other words, there's going to be no carryover effect between rounds other than through what the agents are learning. And one thing you can ask is this a reasonable assumption to make all the time? So just as an example, consider we're playing a game of traffic routing. So all the agents are trying to, go to their destination by picking a route, and they're going to pay a cost related to the amount of delay they face. And they'll face delays if many other agents choose the same routes, say. On the left, you can think about, modeling traffic routing in the case of the morning rush hour traffic. In this case, you might think that's a very reasonable assumption that there really is no carryover effect, because we're going to be playing this game on Monday morning, then Tuesday morning, Wednesday morning, etc. But no matter how bad the morning traffic was on Monday, it'll have cleared up by Tuesday morning, in which case, we're going to play the game again fresh. On the other hand, if you're thinking about traffic routing as modeling, for instance, second by second packet traffic in like computer networks, maybe this isn't such a great assumption, because packets take some time to clear, and then if a packet gets dropped for some reason, then it will need to be resent in the next round. Whereas if it actually was able to be completed, then it wouldn't be present in the next round. So in this latter case, you might think that there's a lot more, of a carryover effect. So the goal of this work is we kind of want to think about this question of what can we say about the quality of competitive learning outcomes in repeated games when you do have this sort of carryover effect. And in particular, we're going to study this question in a very natural queuing setting where this arises. So just to get into the model of queuing that we're going to be thinking about, we're going to have some set of queues and some set of servers in a discrete time queuing system. And so what will happen is that each queue I will receive new packets with some probability lambda I in each round. On the other hand, servers will succeed in at serving a packet with some probability mu j in each round. And what happens at each time step, each queue can choose one server to send one of their uncompleted packets to try and get serviced. So in this case, the first and second queues are trying to both send to this top server, and that third queue is trying to send to the second server. And then what will happen in each stage of the game is that servers can process at most one packet according to that probability mu j. And what will happen is that it'll return all the unserved packets to their queues. So in this setting, or in this example, the packet for the first queue got cleared by that first server, but it's returning the other packet to the second server. And then in the bottom case, that third queue, that server failed. It did not succeed in clearing a packet, so it gets sent back to its queue. And I'll talk a little bit more about how servers kind of choose to break these ties, like in the case of the top server. And what we're going to make the assumption is that queues use no regret learning to kind of selfishly figure out how to select servers to get the best service to clear their packets. And when you have these packets getting returned to their queues, this is the sort of carryover effect we want to kind of better understand. One thing I just want to mention now is that if you think about the one queue many server setting, in that case, there's no competition between queues because there's only one queue. In that case, it's really just a multi-arm bandit problem. It's just a learning problem. And this was actually studied extensively by Krishnasamy et al. In NeurIPS 2016, where they very tightly characterize how the lengths of the queues build up over time. So our main question that we want to think about in this talk is how large should the server capacity be compared to the arrival rates of the queues to ensure that competitive no-regret queues will remain bounded in expectation over time? And just to kind of build a little bit of intuition for this, let's think of the one queue, one server setting for now. In this case, there's really no learning and no competition. The queue just receives packets at a rate of lambda, and it's just whenever it has a new packet that it hasn't been able to clear yet, it sends it to the server where it'll get completed with probability mu. In this case, if lambda is strictly less than mu, one can show very easily that the expected queue size remains bounded uniformly in time. The reason is just that the queue size is really just taking a biased random walk on the half line. On the other hand, if lambda is equal to mu and they're not both degenerate, meaning not both 0 or not both 1, one can show that the expected queue size will actually grow like theta of square root of t with time. And the reason for this is that it's taking an unbiased random walk in this case, and one can show that this is kind of how the expected size of an unbiased random walk will grow. And in the last case, if lambda is strictly greater than mu, then it's not too hard to see that the expected queue size will grow linearly with time. So in this case, there's kind of a sharp threshold for the behavior of what the queue size will be with a function of time. So now back to the case where we have many queues and many servers, the first thing we would like to say is when could a sort of centralized scheduling algorithm ensure this thing that we want, namely that the queue sizes remain bounded? So to do this, just assume that we've sorted the queues and servers in decreasing order. And then a very analogous condition that one can show to the one queue, one server setting is that it's necessary and sufficient for centralized stability in this bounded expectation case that for all k, the sum of the top k arrival rates be at most the sum of the top k server rates. And the reason for this is that, recall that we allow queues only to send one packet per round. So if you think about what's the best thing the k fastest arriving queues can do, well, it would be to somehow use the best k servers. So this is kind of where that condition arises in a very analogous way to the one queue, one server setting. So this is what you need for a sort of centralized scheduling algorithm to ensure that the queues aren't blowing up with time. So now, remember, I mentioned I promised you that I would tell you how servers are going to choose between packets in our model. And there's two natural ways to do this. Option one is just a server will choose between the packets it receives in a round uniformly at random. And the second one is just they'll take the oldest packet it receives first. And so the main results we can show is that in the first case, in option one, when queues use this no regret learning, it need not help coordinate the queues in the sense that their queue sizes might blow up with time, unless if the service rates are much, much larger than the arrival rates. However, if you do option 2, which is that the servers are going to choose the oldest packet it arrives in each round, learning actually will help coordinate service. And all we need for this is actually the service rate to be just a factor of 2 bigger than the arrival rate. Namely, in that condition I just showed you, you can just add in this extra factor 1/2, and then no regret learning will ensure that all the queues will remain bounded in expectation over time. Let me just quickly say something about the first option for why uniform selection fails. Imagine you have one really big queue and one server. So think of the queue as being sized roughly 1 over c for some parameter c bigger than 1, with a corresponding server with rate 1, meaning it'll always be able to clear a packet in a round. And think of having many, many small servers and queues. Those ones, don't worry so much about the numbers, but just think of them as being like theta of 1 over n, say. And I have n queues and n servers in this case. And so, and we impose a slack of c greater than 1. So namely make the servers have a factor of c higher than their corresponding queue. In this case, there's a very simple coordinated way to get everyone to clear efficiently. It's namely each queue should just send to their corresponding server, in which case we're in that 1 queue, 1 server setting from before, where the lambda is much smaller than the corresponding mu. So everyone's queue size will remain bounded in expectation. However, if you have no regret queues, what can happen is that actually some of the smaller queues might say, well, the first server, the big server, is going to be choosing uniformly at random. And so if some number of them actually send up to the top, they'll actually get a little bit better service than what they were getting at their own queue. But that top queue with the rate 1 over c needs to be getting service, at least a 1 over c fraction of the time. So if enough of these small queues saturate the service on the top server, that queue will not be able to clear and it'll grow linearly in time. So the moral is, even with this nice slack, when servers choose uniformly at random, in this case, the big queue will not be able to clear efficiently and it will grow linearly in time. So this is a bit kind of a high level of why uniform selection fails. So now going back to option 2, our main result is that, recall I just rewrote the main theorem here. So the main result is that suppose that servers now instead attempt to serve the oldest packet received in each round as opposed to uniformly at random. And again, assume that queues are using no regret algorithms and that we have this extra slackness factor from the condition we needed. Then the theorem is that all queue sizes will remain bounded in expectation uniformly over time. And actually this factor of 1/2 here is tight. I just want to mention a corollary of this, or rather a slightly more general version of this, which says that with probability 1, all the queue sizes actually grow subpolynomially. That is slower than t to the c for all c greater than 1, where t is time. So now let me just get a little bit into the proof of that theorem. The way it's going to work is to use a potential function argument. And the potential will look something like this. It'll be some potential function phi, which will roughly decompose as a sum of phi taus, where phi tau will roughly equal the number of packets aged tau or older in the system. So with this potential function, we're going to apply a very powerful random processes theorem from P. Mansell and Rosenthal, which roughly asserts that any random process that satisfies both that it's sufficiently regular in some slight technical sense, and also has negative drift when it's large. So the expected increment is decreasing when it's large. Their result says that any such random process will remain bounded in expectation uniformly in time. So with this powerful theorem in mind, what we need to show is that the no regret and that factor of slack that I mentioned will actually imply negative drift of this potential function when the queues have large enough backup. So now let me just give a little bit of intuition for where this potential function comes from and why no regret is helping for this. Suppose that we had some subset of queues that are backing up really badly. They've got a lot of packets that are, say, at least tau old. And let's say for simplicity that the other queues are much younger. They're doing much better. They're not blowing up. In this case, these really old queues will have priority via the scheme because they have very old packets. So servers will always choose their packets to clear over the young queues. And now kind of look at a long window and let's think about what's happening with the best or the fastest servers. It'll either be the case that many of these old queues are sending there throughout this window, in which case that slack condition we had will actually say that the decrease in queue size, that you will get a decrease in queue size. Or it might be the case that, they're not sending there for some reason. But we know that they had collectively had priority over the young queues, and we also know that they're no regret queues. So in that case, the no regret property will assert that they're actually doing really well as well, because again, they had priority at these best servers, and we know they would have gotten good service there. So in either way, balancing these two, this is kind of how you get the theorem. But this only tells you, in this kind of special case, what's happening with the packets that are old. To ensure that you have negative drift, you will need to make sure that the young queues aren't actually growing too fast, or else the potential will rise. So what you need to do is actually apply this at all thresholds tau simultaneously to let you kind of use this no regret condition at all scales. And it turns out if you do this, carefully enough, you'll be able to show the negative drift that we needed. And let me just go into a couple extra technical details of the proof. We actually need no regret to hold on some specific windows of long enough size, and we actually need them to hold with high probability to kind of avoid some really annoying correlations in this process. And like I said, this Pimentel-Rosenthal result has some sufficient regularity conditions that are a little bit annoying to deal with. So one needs to do a couple technical things to deal with that. And very extensively throughout the proof, we use the idea of like deferred decisions or coupling repeatedly. And the idea is kind of to study ages instead of sizes. And this will allow us to kind of, using this deferred decisions framework, apply lots of nice tools like concentration bounds, and again, avoid these bad correlations for the analysis, as well as help out with this sufficient regularity condition from the Pimentel-Rosenthal result. So just to summarize, like I said before at the beginning, learning in games has many nice features, but not as much as known about kind of what the cost of decentralization is in games where you have this sort of carryover effect. And in this simple queuing setting where we have this carryover effect, we're able to show these sorts of stability results for selfish learners. And again, where there's very strong dependencies over time via these return packets and this priority scheme. So kind of future work that would be really interesting is, can these kinds of results be extended to other natural games with carryover? So even within the queuing setting or routing setting, you might think of more complicated routing schemes or feedback structures for the queues. And away from queuing or routing, you can also think of, for instance, auctions with budgets. So if you have a budget and you spend some of it in this period, that's less that you have to spend for the next period. And also this kind of stability property that we show, it's kind of a different qualitative measure than the traditional price of anarchy results. So it'd be very interesting to see if you can prove these other kind of different sorts of qualitative measures of learning outcomes in other games. And with that, thanks everyone so much for listening.